I have a question, Chad.
Sure.
If you don't mind,
So we'll talk about data. Let me share my screen. All right. So today I posted this up recently, so you can take a look at this if you want. You can review it later. So I'm going to be talking about three main data types today, or data structures. So there are stacks, queues, and linked lists. Not all of this stuff is going to be terribly useful necessarily, but this is the kind of like computer sciencey stuff and the kind of things that interviewers like to ask about. So stacks. So can anyone tell me, we have seen some examples, or at least one example of a stack.
Our actual stack of what's happening when we're running the code?
Yeah. So the execution stack, or the register of records, or whatever you want to call it. So as your program is executing, when you call a function, it creates a new execution context, and that's placed on a stack. And then if you call another function from inside that function, then that adds to the stack, right? So you just keep adding up function calls, and then when the function calls, when that most deeply embedded function call eventually returns, then that enables the next function call to return. So you kind of stack things up, and then you pop them off. And the general idea here is that LIFO, LIFO, last in, first out. So if you have a stack of trays at a buffet or something, right? Or plates at a buffet. When you grab a plate from the buffet, you grab the top one. You can't like lift up half the stack and then pull out the one that looks really clean to you, right? You have to take whatever's on top. And same if the employee is putting new plates on, there's a stack, and they just set it down on top of what's already there. So there's only one access point for this data structure. So you put things in, and then you take things out from the same one. We'll look at we'll run through an example, like an example piece of code that uses example program that uses stacks. Queues are similar to stacks, except there are two access points. You can put something in at the end, and then when you take things out, you take it out from the top or the side, or whatever spatial metaphor you want to use. So a queue operates more like a regular line, right? So if I go to the bank, if I'm the first person in line, I expect to be the first person to get helped, right? And the person who's arrived, 3 people behind me, he's gonna have to wait until everyone in front of him has been served before he goes. So a stack would be used. A stack is used for controlling the execution of your program. Queues, queue could be used for let's say you're making a request to a server or something, and the server is overwhelmed, so it might put requests into a queue, for example. So those requests are saved, and they're saved in the order in which they were received, and then the server can, as it has available processing time, can process those requests as they came in. So there's stacks and queues, and then linked list is a little bit different. So this is complex. So a linked list, the unit of a linked list will be something called a node. And we'll see, well, I don't know if we really will get into it, but if you are interested in data structures and algorithms, and you start getting into more intermediate and advanced things, you'll see nodes everywhere. So a node is usually a thing that has a value, like a number or letter or an object or whatever, right? So it could be anything. So it's got like a piece of data or value, and it also will have a reference to some other node. So it's like it's a container that has a value and then a little pointer or a link to the next value. So if you and just a couple of things to note. So one, that every node in the linked list will have that basic structure, but the head node is important because if I want to get this value, if I want to get this third value, I have to start here, right? I have to start here because this node right here doesn't know anything about this third node. It only knows about its immediate neighbor. So if I want to traverse a linked list to find a value or whatever, I have to start at the beginning and I have to go through, there's one path through the data because every item is only connected to one other item and it doesn't know anything about, its neighbor three doors down. So one, you have to have a head node because that's where you start any kind of searching or traversal. You have to start at the head. And the other node that's a little bit special is the last node. So the last node, this pointer to the next node won't be a next node because there is no next node. You can express that however you want, but typically put like a null value or none or something like that here. So
Can you give an example of this seems so esoteric? Can you if I'm clicking on a website and what would happen, or how is this used? I get the first two.
Sure. Yeah. So we'll see an example of that in a sec. So this is a little esoteric, and this is more like it's like recursion, right? It's stuff that is important if you want to be competent at computer science and if you want to do well in interviews, but you probably are not really going to use it in practice, or you're very unlikely to use it in practice. And a linked list solves a certain, like all of these data structures. So why do we have in Python we have lists and we have dictionaries and we have strings and now we have stacks and queues and linked lists. So why do we have all this stuff? Part of it is because each one has its own set of let's say costs and benefits. So they're just specialized tools, and depending on what job you're trying to do, one tool or another might be a more appropriate choice. So learning kind of the tools that are available and why you might choose one over another is important. So we'll talk about a little bit in a sec about linked lists, but hold on to that question. And if at the end you still you still have that question, please let me know.
Cool, thanks.
But yes, we're implementing a linked list is not something you're likely ever have to do in real life. Okay, so let's talk about why do linked lists exist. So we're familiar with arrays, right? So in JavaScript we call them arrays, in Python we call them lists. But the way that lists or arrays are implemented in Python and JavaScript is not entirely. It's not. You could say it's not a real array, or it's not strictly speaking an array. So arrays are a data type that exists, and the strictest definition of an array is something. It's a container and it has a fixed memory slot, or it's a container with a bunch of sub slots in memory, and it's fixed. And it has to be contiguous. So if I create an array, and I have this array here that has 6 elements, strictly speaking, in lower level languages, this is, I think, still the case. You have to specify, you can't just create an array. You have to create an array that has 6 slots, and those 6 slots have to be filled by a floating point, an unsigned floating point integer, and an unsigned floating point integer takes up 8 bytes or whatever. So the computer finds somewhere in memory that fits that specification, and it says, oh, okay, here's where your array is going to go. It's going to fit right here in this slot, right? And then you populate the array and you can do stuff with it. But what happens when you need to add? What happens when you need to add something? So let me back up and say the benefit of the array, one of the benefits of arrays is that it allows basically immediate access to any item. So that's in big O talk. I keep mentioning this. We haven't formally talked about it yet. I can access any element in O of 1 time, which means basically instantly. So it doesn't matter how many items I have in my array, I can access any particular item immediately, right? So if I want to access the 0th element here, I go immediately here. If I want to access the 5th element, I can go immediately to the 5th element. Unlike a linked list, right? So a linked list, I can't go directly from here to here. I have to traverse every single item, right? So if I have 100 things in my list and the thing that I want is the 100th item, then I have to do 100 operations, right? So the number of operations I have to do is directly correlated to how many items are in the structure. So that's called O of n. So n means however many items you have, that's how many operations you have to do. So here you create an array, and the computer, the computer knows the memory address of this first item, right? So it creates the array, it blocks off that space, and it knows the memory address of this first item. So when you go to access the 5th one, all it does is just add, 5. Oh, here's memory slot 30. You want the 5th item, so it's just 30 plus 5, 35, go right here, boom, you have it, right? So the one problem with this, it's a very strict implementation of arrays, is what happens if you want to add something, right? So if I want to add another, I want to append something to the end of this array. Well, what if there's already something occupying the memory in that next slot? Well, then what happens? Well, I can't put it here, and I can't just go around it because arrays have to be contiguous. So I have to pick up all of this stuff and find a new slot that fits the new requirements, create that, and then copy everything over. So if I have, right here, 6 elements in my array, if I have and I add one to it and I have to move it, then I have to do exactly that many operations, right? So again, that's O of n time complexity. So if I have 10 items in my array, I have to make, I have to move 10 things. So this is a downside of arrays. So the upside is once you have it there, it's O of 1 to access. So I get immediate access to any element. The downside is that if I want to add things to it, it's potentially O of n complexity, meaning if I have 100 things in my list, I have to potentially move and copy 100 things. So linked lists. So why do linked lists exist? So again, everything has a trade-off. So arrays are very good for access and not so good for insertion. So if I want to add something to an array, again, this is a very strict implementation of arrays. Actual Python arrays don't really work that way. So here again, so let's imagine that this is your computer's memory, and you have this array. You want to add one more, but they're just the memory is pretty full, and there isn't a contiguous slot. Well, then you're kind of screwed. You can't insert that new thing. So one way to get around this is to use a linked list. So a linked list doesn't require contiguous memory. So I can have a bunch of nodes, and each node can be its own little thing. And because each node has a pointer to the next node, it doesn't have to live right next to it. So if I want to start at one node and say, hey, who are you connected to? You can say, oh, that guy over there. And then you jump over there and you ask that guy, hey, who are you connected to? And he says, that guy over there, and you jump over there. So you don't need this strict requirement for memory. Now, so but this comes at a cost, right? So all these things have trade-offs. So now the issue is that I can insert immediately in O of 1, because I can just, if I know where my head is, I can just have my new node be the new head, right? So I know where the head is, so I insert a new one, boom, that's the new head. So it's immediate. But if I want to, let's say, search for an item or delete an item or whatever, that's potentially an O of n operation. So I might have to traverse every single item in the linked list in order to find what I'm looking for, right? So there's a trade-off. Again, this is just describing linked lists. So, just putting things, you can basically put things any old place, doesn't matter, because they can all point to whoever their neighbor is. So I would frankly take most of this as kind of an intellectual exercise, but that's linked lists. We're going to go ahead and implement all three just so we can see what that looks like. Are there any questions so far?
Yes, where are you getting the 4n, 6n? Is that coming from the array? So the first number 4 is 4n, but then 6n is like way down further, and then you've got 2n is before 6. So
yeah, 4 is just whatever value it contains, whatever data it contains. So like this 4, 7, 2. So this is not, it's not sorted. So the head just happens to be 4, just like the first one. And then this one points to this node, which has a data value of 7. And the data value of 7 points to this node, which has a data value of 2.
So n in this case, it means node. It's not the O of n that you were talking about earlier?
Correct, yeah.
When we were doing the node exercise a couple of days ago, that's not this, because that had two, the left and right one.
Yeah, so yeah, that was a binary tree, but it used nodes. So a linked list is actually a simpler structure than a binary tree, but they both use nodes, right? So you have this unit called a node, which is found in a lot of different data structures. So a binary tree, I mean, you can have, there's all kinds of specific terms for very specific variations on trees or graphs. I think graph is the more general term. Tree is a specific kind of graph. Then you have, it's just one of those things where you can get very in the weeds with it. But the basic idea is that you have node, and then a node is connected to some other node or nodes. Okay. So let's go ahead and make a stack. All right, so let's do zoom in. Okay, so a stack, all of these data structures will have kind of basic requirements and then some other maybe secondary methods. But the basic things that we need for sure are, we have to have a method for pushing and we have to have a method for popping. So let's create a stack class. We have stack, and then we'll create our push. All right. So we have a class now. It doesn't do much, but this is the real class. So one decision, I guess maybe the first decision we'll have to make is, what do we want to use as our underlying data type? So we could use, we could use a string, we could use an object, we could use our own custom, again, another custom data type that we use, but I think the easy choice would be to use an array. So we'll do that. Oops. So under the hood, basically our stack is going to be a specialized list. It's going to be a specialized Python list. So what is a push operation supposed to do?
That put something at the end of the array?
Yes, yeah. So again, it depends on, whatever metaphor we're using for it, but yeah, on the only end that we can do stuff to. So how do we add something to the end of a list in Python?
Use the append method.
Okay. So for my push, I'm probably going to want to accept a thing. And then I'll do self.base.append item. So if you're wondering at this point why this seems so stupid, that's fine, because all we're doing basically is renaming push to renaming append to push so far. But we'll see how, it's potentially a little bit more than that.
Is there a reason that you're calling it base?
Not really, no. So pop. Okay, so now let's just try seeing if this works. Let's create, how do I create an instance of a stack?
You need a variable.
Okay.
And then equals stack. And do you need to put item in there? No, that's when you use the method, right?
Yeah. Okay, so I'm creating instance of stack, and then if I want to add stuff, All right, and I can see what's happening. So run this. So now I have 2, 5, and 9. So what did I put on first? What was the first thing in?
2.
Right. So, and then the second thing is 5 and 9. So if we're going to remove things, where do we need to remove them from?
This is the stack. We're going to take it off the top. So it'll be
Yes.
the last one in.
Exactly.
Well, the end.
Yeah. So it'll in this case it'll be 9 that we would remove first. So we can implement this self dot base dot pop. So again, we're just not even really renaming the Python method this time, but so we'll return. So pop is typically returned. So now we have a stack. So we can push things onto its end, and we can take things off from its end. So let's try popping something. S dot pop. Right, so we added 2 and then 5 and then 9, and we removed it. 9, the most recent thing we had added, is removed. So that's basically it. I mean, there are other methods that are more like helpers, but this is the basic idea. So why would you do anything like this? Well, so what if we want to loop over our stack? Let's do for Does anyone have any guesses? So our base is just a Python list, right?
We're only doing almost a make-believe stack, so you can just use the standard features we've done in the past to loop over it, right?
Sorry, what? Can you say that again?
Well, it's a list. It's not a real stack, so we can loop over it the way we've always looped over it. Or I mean, if you want to treat it like a real stack, you can pop everything off and put it on a new stack.
Yeah, so we could directly access. So let me do this. So that will make it a little harder for us to directly access. Yes, this is not gonna. I just broke that, but that's fine. So does anyone have any theories on what is going to happen when we loop over our stack?
I think as we've defined stack, we don't know like what the iterable is. Like this class is just the push and pop method that are accessible from outside of it.
Mm-hmm.
So we can't access anything that's like an iterable.
Okay.
So you can't loop through it.
Okay. I think that's a good hypothesis. So we talked about iterables last class. So this class doesn't implement Dunder iter. So let's see what we have to try to run it. Get a type error, stack object is not iterable. All right, it's not iterable, even though this, under the hood, what we're using to keep everything, to store everything is a list, which is iterable. Our class is not iterable. So we have the same issues. We're going to s dot insert. Like that. Again, so insert is a list method in Python. Pretty sure that it is. But when we try to call that on our stack object, we get an attribute error. Stack object has no attribute insert. Right. So what we've done is we've created our own custom thing, but it only does exactly what we want it to do. Right. So we've made a more specialized tool. So we don't want our stack. We don't want people to be able to insert things in the middle of the stack. We don't want people to be able to loop over the stack. So we just implement exactly what we want. So that makes it a more precise tool. So that's one reason why you might want to do this kind of silly stuff, because you could just treat an array like a stack, right? Only call append and pop. Okay. So we'll look at 635. So Q is basically the same thing. I'm going to let you guys, you can implement that on your own. So for the challenge, you'll be doing that. Let's look at linked list. So again, linked list, just to refresh ourselves. So a linked list is a complex data structure. It's got a node, and each node will have, a thing, whatever, a value, a piece of data, and then a reference to the next node. So the first thing, if you want a linked list, is we're gonna have to make a node. So let's do. Jared, can you help me write a node class?
It'll be class node.
Okay.
And then define double under init.
Okay.
Self and let's see.
So each one
looks
will.
like it has a value.
Yeah. Mm-hmm. Okay.
And then a reference to the next node.
Okay. So we'll handle this first. So I'll call it data just because the slide does. And then so there's more than one way to implement this, but the way we'll do it is when you first create a node, it doesn't know anything about what it's connected to. So we'll start it off. The next reference will be none. Okay. So we have a node. I think this is all we need. We have a node. So now we need a linked list class. So we can do linked list. Oops. We have a linked list class. And if we look at our diagram here, so at the very bare minimum, linked list is going to have a head node. So that's probably a good thing to have in the init. So again, there's more than one way to do this, but and we'll do we could create a new node here and maybe have self.data be none or something. I'm just gonna make this none. I guess that's technically not really the pattern, but it'll make this a little easier. So we'll do, the head will just be none for now. And then we're gonna need to implement some other methods. So we can think of methods that we might need in our linked list class. So we can think of insertion. That's probably going to be an important one. We'll need an insert. I mean, there's a whole bunch we could think of. We could do search. We could do get the length or the size. So I'm gonna not do all of these because again, that's part of the challenge, but we'll look at insertion for now. So def insert. So we have a couple different ways to handle insertion. We could either, create a node and then pass in the whole node to be inserted, or we could just pass in the value, the data, and then create the node here. So either one is fine. I'll just create it here. So we'll create a new node. We have node, and then we'll pass in whatever, we'll call it data. Okay, so when we call insert, we create a new node. Now, what we're going to end up doing, let me see, another, let me pull this over here. All right, so here's just another image of what a linked list is. So here we have a node, right, which has a data member and then a reference to the next node. And here's the head. So this is the head node, and then so on. And then this points to none or whatever we use to indicate the end. And what happens when we insert, so we have all these nodes here. When we insert, we could potentially insert at the very end, right? But that would kind of defeat the purpose of the linked list. So we'll insert at the beginning. So what we do is we create a new node, and then we make the new node the head, right? So we create a new node, we make the new node the head, and then we say, new node, your next is the previous head. So this is all a little confusing, but what we're doing is we have let's say this is our previous head, right? And we want to add a new node to our list. So we create this new node. Now this becomes the head, right? So now this is not the head anymore. This is the head. And we point the current heads next to the previous head. So we have a list, we have, 1, 2, 3, we add 1. So everything just shifts over basically. So we're going to create a new node, and then we're going to kind of create a temporary reference to the old one, so we don't lose the original head node here. So we'll call that old head is self.head, and then self.head is the new node. Right? So now I've replaced this, but the old head is still just floating around in space. So I need to make sure that that's still, still accessible within the linked list. So what I have to do is say, okay, so we have a new self.head, we have a new head, but I have to say, head, your next is now the old head. So self.head.next is old head. So it's it's a bit weird. It's kind of a tongue twister. But let's try creating a linked list. So I'll print the head here. And it's none, which is what I expect, right? So I just created an instance of the linked list and the head starts off as none, and that's what it is. Okay, so now I'm gonna add another node. So, and I want the value to be, I don't know. All right, so now I'm gonna print the head. Okay, so can someone tell me what's happening here? Why is this printing all this gobbledygook?
Because when we assign old head to, or the self node is a instance of a class.
Yeah,
So it's an
exactly. So what if I want to, what do I do if I want to see this?
dot data instead.
Exactly. So self.head.data. Right, because self.head is an actual node. So if I want to see the node's data, I have to access the data. So the linked list heads data is first node added. Okay, so that's fine. But what happened to the old head?
You mean like that's gonna get called next? Is that what you mean? Like what happened to it?
Yeah, so I guess, is there any way for me to access it?
Can
Is it
you,
old head?
Sorry?
Go ahead, Jess.
I was thinking if you do print ll.oldhead.data.
Okay, so ll dot.
Wouldn't that be none at this time though?
Well, yeah, so old head should probably be none, but so maybe what I'll do is I'll do this more properly, and I'll do node like that. Okay, so if I look for my linked list instances old head, what am I going to find? I mean, if I look for this property,
it doesn't exist.
right? So it exists here. So what kind of variable is old head here?
It's a local.
Yeah. So in a class, we have three kinds of variables. We have local variables, which old head is just a local variable inside this function. It only exists inside this function. We have instance variables, which are accessible anywhere within an instance, like self.head. And then we have class variables, which we don't have any class variables, but right. So those are the three kinds of variables. So you can't directly access an instance, or sorry, you can't directly access a local variable from an instance. So we can't do that. Is there any other way that we could access the old head?
It's referenced through the new head's next property.
Okay, so self.head dot next. Let's see what that is. Okay, so it's another node object, and notice that it has the same memory address as this. So this node that we created initially, that was the head, it's been moved. We're now referencing it instead of ll.head, it's ll.head.next, but it's the same thing. We've just changed how we access it. So if I want to see the value, and we see that it's none. So if I had 30 things in my linked list, I would do ll.head.next.next.next.next.next.next.next, whatever, however many times. Because this is the only way you can access anything. The 30th item in the linked list, you can't access it directly. You have to go through every single previous node. So the only way to get to here is start here, go here, go here. There's one path through the data. So if I wanted to search, I won't actually implement that, but if I wanted to search, you can kind of break down that process as you have to start at the head. You always have to start at the head. And then you ask yourself, is the data that I'm looking for match this node's data? If so, then you're done. You can return whatever you're going to return. If not, you have to ask, does the current node I'm looking at, which will be the head initially, does the current node I'm looking at have a next property, or is next none? If next is none, then you know you're at the very end of the list. So if you haven't found it and the next is none, then it's not in your linked list. But if the next value does exist, then that means you just move over to this node. So this node is now your current node. And you ask yourself the same series of questions. Is this node's data item the information I'm looking for? If it is, then you're done. If not, you have to look at the next value. Is it none? If so, then you're at the end of the list. If not, then you move on to this one. And this is your new current node. And again, you check the data. Is this the data that I'm looking for? If so, then you're done. If not, then you have to look at the next, and so on and so forth. So you can solve that either iteratively or recursively. Okay. So why don't we take a break? Let's take a break till 7, and we come back. I will give kind of an example of using stacks. All right, so we're gonna implement basically file, like let's say you want to write an essay or something, and you write a line, and then you want to be able to undo that line later. So we're gonna implement something that allows you to write lines to a file and then undo the lines and rewrite them. So we're actually going to use 2 stacks for this, and I'm gonna just walk through how it works. So here are the 2 stacks. Here's the main stack, which we'll call the history, and here's a temporary stack, which we could call something else if you wanted to. And then the way this works is, say this is my first edit, right? So I'm writing lines. This is my first edit, my first line. I put it onto the history stack, and then I write that to the file. This is the page or the file we're writing to. And then I write my second line. I save that to the history stack, and then that goes right here. And then the third line, I do the same thing, right? I add the third line to the stack, and then this line gets added to the page. And then I have, well, okay, so I write this line, then I add it here, and then I realize, you know, this was a bad line. I want to undo this. So the issue is, how do you go about undoing this? So we have this stack here, right? And we can take this off of the stack. Maybe we can take this off of the stack, and then we can get rid of all that stuff, and then we can rewrite the file, maybe, right? Rewrite the file, but then we get, oops. We get this, right? So it's in the reverse order now. So when we put stuff on a stack, of course, we put it on in one order, and because it's first in, or was it last in, first out, when you pull this out, it's going to be in reverse order. So how do we solve this problem? Well, one way is to use another stack, right? So if one stack reverses it, then two stacks will reverse it again. So let's look at another implementation where first we go here, and this gets written, and then the second one right here, this gets written, and then we write our dud line we want to get rid of. Okay, so now this is a dud. So maybe you can delete this. And what we're going to do is we're going to just get rid of the dud. But before we write to the file, we're going to put this into the temporary stack. I'm going to pop everything off the history stack and put it into the temporary stack, right? And then what we're going to do is from the temporary stack, we're going to write to the page and then put it back on the original history stack where it was. And then we'll take this, put it right here, and then put this back on the history stack. So now we're back where we started before we had our dud line, right? We have two things on our history stack in the proper order, and our page is displayed, the lines are in the right order. So this is what we're gonna try to implement. So I have some of this pre-written. So we're gonna use a stack. I have some other additional methods, but you can, So this is just a stack. It's very similar to what we were doing before. So I'm gonna say, I'm actually gonna write to a file here. So for my init, I want to be able, when I create an instance of this undoable thing, I'm gonna create it with a file name. So and I'm gonna need to create these two stacks, right? So I have two stacks. So my instance is gonna need two stacks. So self.history. And then we'll do self.temp. I'll call these stack. Okay, so now when I create an instance, I will have the file name. That's like the file I want to work with, and then these two stacks. So the first thing to do is probably to implement the write file operation. So to write a file, we've seen this once, we haven't really officially talked about it yet. So the order, if we recall here, the order is basically, so I want to add a new line. I want to write a new line. So I first add it to the history stack, and then like make a copy or whatever, and then print it to the page or add it to the page. So we'll do that. So the first thing I'm going to do is the write file is going to need to take a line. This is the line that I want to write. And I'm going to add whatever that line is to my history stack. So self.history stack dot push line. So if I call this function to write a line, I will first push it onto the history stack. And then when it's on the history stack, I will write it to the page. So to write a file, we'll see more of this in the next week or so with open, and then this will be whatever file name we want. And we'll say that we want to append, that's an option. So instead of rewriting the file, we'll append, so we can just add one line to the end without overwriting everything that's already there. So this open file, we're going to call F. So again, we're not concerned with the details here, but F dot write, and we'll write the line. And then we'll also write a new line. This is just formatting. It's not really important. All right, so let's see if what we have so far works. Let's create an instance. Okay, and pass it a file name. So so we create a file, and then we'll do write file, u.write file, and something like so we'll save this and run it. And notice I have this new file here, and whatever I wrote is right there. So I'll just delete this. And I can make sure that I actually have something on the stack. So just this, we wouldn't want to use this, but we wouldn't want to do it this way, but u dot history stack dot. There's the underlying array that I'm using just to make sure that that's actually in there. Okay, so we have the line on our history stack and it's written in the file. Okay, so that's we're done with writing. Now we need to undo the write, which is the hard part. So if we look back at the diagram, so how do we right? So I have a bad line. So what I want to do is take the bad line off of the history stack and then take whatever is on the history stack and put it onto the temp stack, delete this file, and then start that process over again. So put this back onto the history stack and also write the line to the file for every single item that's in the temp stack. So the first thing we're going to do is pop off the history stack. So self.history stack.pop. Now whatever our bad line is should be gone. We don't need to do anything with that. It's just gone. So we just pop it off. Then what we have to do is somehow get everything from the history stack onto the temporary stack. So we just saw that we can't use a for loop, right? I mean, that would be a typical thing to do, right? So for whatever items in this array, do something to those items. You can't do that. We have a couple other of these helper methods, which can be useful. So we can use, we actually use a while loop, and we can use is empty. So you can do while not. Let's do, yeah, it's history stack. While not, tell the history that is empty. So while there's still something on the history stack, what we're going to do is we're going to pop it off. And then what we're going to do is we're going to push it onto the temporary stack.
Do you need parentheses on 31 after is empty?
Yes, thank you. So we popped off, the most recent addition that we don't like. And then we're going to check while there's anything on the history stack, pop it off and put it onto the temporary stack. So that's going to get us, so you take the dot off. Let's do first and second. So we took off the dot, we popped it off. Then while there's anything on the history stack, put it on the temp stack. Okay, so now we're here. We have the stuff on the temp stack. So what we want to do now is whatever is in the temp stack, like while there's anything in the temp stack, what we're going to do is write it to the file and put it on the history stack. So because we're going to need to do a file operation, I'll use the with to create context. We can talk more about that later. So with so this time I'm going to so the specifics of what we're doing in the file, don't worry about that, but we're just going to write all the lines here. And then we'll do let's see. Yeah, okay. So we're going to open the file, and then we're going to have a while loop similar to what we did. So just like we emptied the history stack, we're going to have to empty the temp stack. So while self that temp stack that is empty or not. Then what we're going to do is we're going to get the line. So for every line will be self dot temp stack dot pop. We could, yeah, temp line, we call it history, whatever. We'll just call it line. So line, we're going to pop it off, and then we're going to push it onto the history stack. And then finally, what we're going to do is we're going to write these lines. So dot write lines. Again, don't worry about the specifics here. That should work. So let's just, so right now we have, let me delete this file. So we write a line, right? And let's write, we know that works. I'll write another line. Yeah, actually, we'll go ahead and delete this line. So u dot undo write, and then write file. So if we do this, we run this. And now we only have this one. So I can add another, let me just do another one. You can see. Delete the file again. And run it. We can see that it's this one that got removed. So again, diagram here, we have two stacks. So stack, you put stuff on, it will come off in the reverse order. So we're using two stacks in this case. And that's basically it. So kind of a, a little bit of a silly example. That's one way to use the stack. Are there any questions about that?
In your diagram, like when you had like 1, 2, 3, and then dud,
Yeah.
you cleared the whole page to get rid of dud and start over. Do you have to clear the whole page, or could you just pull dud off?
Well, yeah. So I mean, I'm keeping the file operations simple. So but yeah, it would definitely be a pain. I'm sure you could do it. You'd have to.
Okay. So it is intended like how you showed it then. Okay.
Yeah.
So okay.
Yeah.
In order to do those operations you just did, we have to have all that code above it also.
Right here, the stack.
Yeah, all that, it's like you have all that code above it. Yeah, all that above it. Yeah.
The
You have
stack
to have all
class.
that above it in order to do the undoable and the writing.
You have to have a stack class because this undoable class is using.
Okay, the stack class, and you have to have the push, you have to have the push, the pop and the peak. And
Well, in this instance, we're not actually using peak.
Okay.
Peak is often part of like a standard implementation of a stack.
Okay.
That's it. So I would think of this largely as exposure. So yeah. So the challenges for today, let me stop.